Hello. In this problem, we have a ball of steel that weighs 50 grams and it's placed in a spring-loaded launcher. So let's first start by writing our givens step by step. So now we know one thing about the ball, which is the mass. The mass of the ball is 50 grams. And the second thing we're being told is that the constant of the spring inside the launcher is equal to 30 newtons per meter. So the spring constant denoted by K is equal to 30 newtons per meter. The scenario here is that when the ball is pulled back 50 centimeters, then released, the ball leaves the launcher at a speed of 10 meters per second. So again, let's list whatever we can tell from this piece of info here. We have the change in the compression of the spring of 50 centimeters. And also we have the final velocity of the ball is equal to 10 meters per second. So that's the first step to initiate the problem solving. The question now is how much work was done by friction in this process. So let's try to understand the process very well so that we know how should we calculate friction and know how much work was done by this force. So when first the ball is compressed and the spring is compressed, potential energy is being stored and it increases. And when we release the launcher, the potential energy rapidly shifts to become kinetic energy stored in the motion of the ball itself. So the point is, if we calculated the stored potential energy in the spring itself, and afterwards we calculate the kinetic energy of the ball when it leaves the launcher, if there is a difference or there is energy lost in the process, then this energy is definitely lost due to friction. And in that case, this will be the work that is done by the friction. So to begin with, now our target is to calculate how much potential energy was initially stored in the spring. So to calculate the potential energy stored in a spring, we use the formula half K, where K is the spring constant, and then x squared, where x is the distance of compression. So let's plug in numbers right now. We have this 1/2, and the K is 30 newtons per meter. And finally, we have the distance of 50 centimeters. But let's be careful here, because to be consistent with the SI units and with our units here for the spring constant, we should transform first the units of distance from centimeters to meters. So 50 centimeters divided by 100, so we have now 0.5 meters. So we will use this instead. So now we have 0.5 squared. Calculating this gives us the initial stored potential energy of 3.75 joules. The second step right now is to calculate the kinetic energy of the ball after it leaves the launcher. So here, the kinetic energy of the ball, that is equal to half the mass of the ball multiplied by the velocity squared. So here we have the half as it is, and then the mass. And you can see that here we have the mass given in grams, but again, to be consistent and to have energy for units of joules, we have to convert this mass to be in kilograms instead. So dividing this by 1000, we find out that the mass of the ball is 0.050 kilograms. So using this here, when substituting, we multiply by 0.050 multiplied by the velocity squared. It's already in meters per second, so no need to convert the units here. And we find out that this is equal to 2.5 joules. So now we have these two energies together, and we need to see, or you can obviously see that there is a difference, or in other words, there is energy that is lost. Now we need to calculate the change in energy, and the change in energy in that case is the potential energy of the spring minus the kinetic energy of the ball. So this is equal to 3.75 minus 2.5, and we have the answer of 1.25 joules. So this difference right now is the work done by friction, or the work lost due to friction, and the final answer for this question is this in my green box here, 1.25 joules.